Welcome to the deep dive. You send us your sources, and we're here to pull out the crucial knowledge without overwhelming you.
Exactly. Think of it as getting the cheat sheet for understanding something complex, really highlighting what matters and, why.
Okay, so today we're diving into a research article you shared. It's titled A General Mass Lumping Scheme for the Variance of the Extended Finite Element Method.
Right, and it's from the International Journal for Numerical Methods in Engineering. We'll make sure the DOI is available if you want to dig deeper later.
So, your mission, should you choose to accept it for this deep dive, is to get a handle on a new strategy. It's used in engineering analysis, specifically within something called the Extended Finite Element Method, or XFEM.
Yeah, XFEM. It's a pretty powerful tool they use for simulating really dynamic stuff like impacts, explosions, things happening very fast. We want to give you the core idea without getting totally lost in the weeds, the really dense technical bits.
Right. So imagine trying to digitally recreate something happening incredibly quickly, maybe a crack appearing and spreading through a material. Uh-huh.
Normally, you'd have to keep redrawing your digital model as that crack moves. That's called remeshing, and it can be a real pain.
Yeah, time consuming.
Exactly.
Yeah.
So XM is sort of a clever way around that. It lets engineers simulate these breaks, these discontinuities inside the material without all that constant redrawing.
It's really useful for those the simulations, but there's a catch. Even though XFEM is great, it can hit a snag.
Okay.
When a crack in the digital model gets really, really close to the edges or corners of the little computational blocks, the elements, it can seriously mess with the calculations.
How so?
Well, specifically, the time steps you need to take to keep the simulation accurate have to become incredibly tiny.
Ah, and if the time steps are tiny, the whole simulation takes forever to run, right?
Precisely.
Yeah.
It can completely negate the benefit you got from using XF in the first place. And that's where this idea of mass lumping comes into play.
Mass lumping. Okay,
Yeah.
so it's like simplifying how the weight or mass of the digital model is handled to speed things up. That's the gist of it. And this research paper we're looking at introduces a brand new way of doing this mass lumping, specifically for the parts of the model where XFEM is actively modeling the crack,
And the goal is?
to make these really complex simulations of fast events much more practical, more efficient.
Okay, now here's where you mentioned something intriguing earlier. This new approach might actually use zero or even negative weight in its calculations.
Yeah, that's the really counterintuitive part. Zero or even negative mass values.
That sounds completely weird. How does that even work? Let's try and unpack that.
Okay, so to see why they do that, we need to quickly touch on how mass is represented in these simulations. Engineers use something called a mass matrix.
Right, to show how mass is distributed.
Exactly. Now, for speed, especially in these super fast dynamic simulations, they often prefer what's called a lumped mass matrix over a consistent mass matrix.
A lumped matrix. So instead of being spread out evenly, the mass is kind of concentrated at specific points, the nodes making the math quicker.
You got it. Think of it like, instead of weighing every single tiny bit of a structure, you just estimate the weight at the main connection points. Much faster.
Makes sense.
BUT. Here's the problem again. When we use XFEM for dynamic events, and that crack gets really close to those connection points, those nodes, in our digital model.
The critical time step issue comes back.
Exactly. That a critical time step, the biggest time jump the simulation can take while staying stable and accurate, can suddenly become vanishingly small.
So the benefit of XFEM not having to redraw the mesh is almost wiped out because the simulation just crawls along.
Precisely. And that's the challenge this paper tackles head-on with this new general mass lumping scheme for those XM bits, the enriched elements.
Okay, so what's the core idea of their new scheme?
The main goal, the guiding principle, is to make absolutely sure that the energy of motion, the kinetic energy, is perfectly preserved when parts of the material are just moving rigidly.
Rigidly, like moving without stretching or deforming, just sliding or rotating.
Exactly. Like a broken piece just sliding past another piece. They want the simulation to capture that movement's energy correctly.
Okay, I can see why that's important for realism.
Right. And this is where the weird part comes in the zero or negative mass for the enriched degrees of freedom.
Those are the extra math variables XM uses just for the crack, right?
Correct. The researchers figured out that to perfectly preserve that kinetic energy for rigid movements, their new lumping method might need to assign zero or even negative mass values specifically to those extra crack variables.
Negative mass. I'm still stuck on that. How is that physically meaningful?
Well, it's not really physical in the sense of weighing something. It's a mathematical construct within the simulation framework. Think about an element one of those calculation blocks that's completely split by a crack.
Okay, broken in two.
What their strategy does is essentially lump all the mass of each broken piece onto the regular connection points, the nodes, on that same piece.
All right, so the mass stays with its chunk.
Yes. And crucially, for that fully split element, they assign a mass of 0 to those special enriched degrees of freedom, the ones just describing the crack opening.
So the crack variables themselves become weightless in that specific scenario?
That's the key insight for a fully separated element. The payoff is huge. It conserves the kinetic energy properly when the two pieces are just moving, rigidly sliding past each other without creating false energy transfer across the crack surface.
I see. If the crack variables have zero mass, they can't artificially contribute to or transfer kinetic energy just because the pieces are moving. That makes a kind of mathematical sense.
Exactly. It prevents the simulation from inventing energy flows where there shouldn't be any.
Okay. So they have this possibility of zero mass. Does that affect how they run the simulation step by step?
It does. Because of this potential for zero mass entries in the equations, they use a special time-stepping technique. It's called explicit-implicit integration.
Explicit-implicit. It sounds like a mix.
It is. Think of it like using different gears. For the regular parts in the model away from the crack, they use a fast, computationally cheap, explicit method.
The standard quick way.
Right. But for the enriched parts, the elements with the crack variables, potentially with zero mass, they switch to a more stable but usually more computationally heavy implicit method.
So they use the fast method where it's safe, and the more robust, careful method right around the tricky crack areas.
Precisely. And the clever part is, because the number of elements with cracks is often much smaller than the total number of elements in the whole model.
The overall simulation speed stays pretty good.
Yeah, it remains quite efficient, often close to the speed you'd get with a purely explicit method, but without the time step problems near the crack.
That sounds like a really elegant compromise, getting the best of both worlds.
And another significant plus is generality. The researchers designed this mass lumping scheme to be applicable to various variants of XM.
Meaning it doesn't matter exactly how an engineer implemented the crack modeling part of XM.
Largely, yes. Regardless of the specific enrichment functions used, the underlying principle of this mass lumping should hold.
That makes it much more broadly useful, potentially.
Definitely. And perhaps the biggest win. By treating those enriched crack parts implicitly, they managed to keep the simulation's critical time step stable. It remains similar to what you'd have for an undamaged element.
So no more drastic drop in the time step size when the crack gets near an element edge or node.
Exactly. It avoids that crippling slowdown that plagues other approaches in the same situation. That's the core problem they solved.
Okay, so they have this theory, this method. How did they prove it actually works?
Good question. They validated it using several benchmark examples. These are like standard test cases in computational mechanics, problems with known behaviors or experimental results that engineers use to check if a new simulation technique is accurate and efficient.
Putting it through its paces.
Right. They started simple, with one-dimensional element like a bar with a crack, and they showed how the mass is lumped to the nodes on either side, and the enriched degrees of freedom get zero mass, just like we discussed. It confirmed the basic principle.
A foundational check.
Then they moved up to 2D elements, triangles and quadrilaterals that were fully cracked. Again, same logic. Mass of each piece lumped to the nodes within that piece, zero mass for the enriched DOFs. They included a figure 1 in the paper showing these examples.
Visualizing the cracked shapes helps.
And they didn't stop there. They generalized it for basically any complex element shape with multiple nodes and a crack running through it.
A general case.
Yeah, they talk about partitioning the degrees of freedom, the variables into those associated with each side of the crack, and then the separate enriched ones. And the conclusion was the same. You get optimal kinetic energy conservation by lumping all the mass to the regular nodes and setting the enriched mass terms to 0 for these fully cracked scenarios. Figure 5 illustrates this general setup.
So that zero mass for the enriched part seems really fundamental to their approach for preserving energy correctly.
It does seem to be the key mathematical insight for rigid body motion in cracked elements. They even detailed the specific mathematical conditions for this energy conservation, referencing equations 27 to 36 in the paper, ensuring the lumped mass matrix satisfies these conditions.
Okay, they definitely backed it up with math.
Absolutely. And they also clearly outlined the steps of that explicit-implicit algorithm they use, how the two methods work together at each time step. That's in section 3.
So the theory is solid, the algorithm is defined. What about the results from those benchmark tests? Did it hold up?
Yes, and quite impressively. Figure 6 is particularly telling. It plots the normalized critical time step, basically, how stable the simulation is against the crack's position within an element.
And what does it show?
For their proposed lumped mass matrix, the line is pretty flat. The critical time step stays stable, sometimes even slightly better than for an intact element, no matter where the crack tip is located.
Wow, okay, that's a direct visualization of solving the main problem.
Exactly. And they contrast it sharply with the traditional consistent mass matrix approach. In that case, the graph shows the critical time step plummeting, just diving down as the crack gets near the element boundaries.
A really clear difference.
Then they showed results for specific problems. First, a rectangular block with a crack that gets hit by an impact. Figures 7 and 8 show stress waves moving through it. Their method accurately captured how these waves traveled and reflected off the crack's surface, crucially, without spurious energy transfer across the crack. It outperformed other lumping techniques they compared against, and Table 2 confirmed the stable time step was independent of the crack location.
So accurate physics and stable speed.
Next up, they simulated a famous set of experiments called the Kalthoff experiments. It involves an edge-cracked plate under impact loading.
A well-known test case.
Right. Figures 9 through 12 and Tables 3 and 4 cover this. The key finding here was that their method could simulate the crack actually growing and propagating without the simulation getting stuck or needing tiny time steps, just because the crack tip got close to the element nodes.
That's huge for practical fracture simulation.
Absolutely. They got accurate predictions for the crack path and propagation angles, and critically, the computation time was significantly reduced compared to using a consistent mass matrix, simply because they could use a much, much larger stable time step.
Saving potentially hours or even days of computation time.
Easily. Finally, they simulated a compact compression specimen test, figures 13 to 16, Table 1. This showed the method worked with different variations of XFEM. They mentioned SX and NX specifically.
So confirming that generality you mentioned?
Yes, and showing it could handle complex, curving crack paths, even in a non-uniform mesh, which is more realistic for complex parts. They did note some minor differences in the crack length history between the SX and NX variations, which is more of an internal XFEM detail.
So it seems robust across different setups.
The overall conclusion drawn from all these examples is pretty strong. This new mass lumping scheme provides a robust, accurate, and, importantly, efficient way to perform dynamic simulations with XFEM, especially when cracks are present.
And the key is maintaining that stable and optimal critical time step, regardless of where the crack happens to be.
That's the core benefit.
Okay, let's try and wrap this up then. This deep dive into the paper shows us a new technique for handling mass in XFEM simulations.
That directly tackles a major bottleneck, especially for dynamic events like impacts where cracks are involved.
The key benefits seem to be accurate energy conservation for moving parts.
Applicability across different types of XFEM implementations.
And the big one, keeping the simulation stable and fast by maintaining an optimal time step, which means huge efficiency gains.
Exactly. It makes these powerful simulations much more practical.
And this really gets to what our listener wanted, a clear picture of a complex, cutting-edge technique without getting totally bogged down in every single equation.
Hopefully, yeah.
Yeah.
You should now have a good sense of how this method works and why it's a significant step forward in computational engineering for fracture mechanics.
So here's something to mull over. If engineers can now simulate cracks forming and spreading much more reliably and, crucially, much faster, what does that mean for the future? Think about designing safer structures, aircraft, buildings, cars, you name it. Does this open up new possibilities for predicting failure modes much earlier in the design process?
It certainly could.
Yeah.
Faster, more robust simulation allows for more design iterations, more complex scenarios to be tested virtually. It might lead to lighter yet safer designs or better predictions of lifespan under stress.
It really pushes the boundary of what we can analyze and potentially prevent.
It definitely raises interesting possibilities for optimizing designs against fracture and impact.
Well, if you're intrigued and want all the mathematical formalism and further details, we absolutely encourage you to look up the original paper.
And as always, keep sending us your sources. We love digging into these topics you bring to us.
Thanks for joining us for this deep dive.